Hello, in this video I would like to present some examples of what I call the unreasonable effectiveness of statistical mechanics and more especially of the Boltzmann distribution. So statistical mechanics is concerned with the behavior of large number of particles, and you want to get some properties of such systems which have many particles without necessarily looking at where all the particle goes individually because you have too many of them. And in statistical mechanics, one of the most amazing result, I think, is the Boltzmann distribution, not to be confused with the Maxwell-Boltzmann distribution, which tells you how fast molecules go in a perfect gas, but the Boltzmann distribution without the Maxwell in front, which states that the probability of having a particle in a state I, so whatever state the system is, that you can describe what describes the system, is proportional to the exponential of minus the energy of the system divided by kBt, and kb is the Boltzmann constant and T is the temperature, and it 1 over kBt is often noted beta to simplify calculation without having to keep these radicals, not these radicals, but these fractions in the exponential. And it can be proven that this distribution is a distribution that maximizes entropy in systems in which the average energy is constant. So this distribution can be useful when you have systems that are in contact with a large thermal bath, so that essentially the temperature of the system can be said to be constant. Oh, and by the way, this is at an equilibrium. I forgot to say, but this is equilibrium statistical mechanics. If you're out of equilibrium, of course, you can have system in very different energy states that don't correspond to this distribution. Now, getting back to our systems that are at equilibrium, we can consider often what happens with some part of the system, just basically what are the distributions in the small part of the system, considering that the rest of the system can be considered a thermal bath. So for example, let's say you have a gas in an enclosure. We can say, well, what's happening to some of the gas molecules? And you say, well, the old gas is in equilibrium at a certain temperature. So basically you have this whole enclosure and you say, well, what's happening in there? And you consider that everything else is a thermal bath. So that's very helpful in many situations. Basically, whenever you have a very large number of particles that are in equilibrium at a constant temperature, you can use the Boltzmann distribution. And in this video, I want to present two results that can be obtained using this distribution. Before I go with the first example, which would be the law of atmosphere, I forgot to mention that the Boltzmann distribution applies to classical systems, that is, systems in which we can track the particles. So for example, ideal gases in which the molecules are spread apart from each other, or solids in which we know that each atom stays at the same place, and other situations. If you get into situations in which quantum effects related to the particles are essential to the behavior of the system, which means that the particles themselves behave quantum mechanically, then you used to use after statistics. Now, this is not to be confused with the fact that the energy levels can be quantized. There can be quantification of each of these energy levels, and the Boltzmann distribution will work. But what we don't want to have is the particles interacting together so that we have to use quantum statistics to deal with their behavior either as bosons or fermions. So the first example is the law of atmosphere. That atmosphere basically describes the pressure distribution in a gas around a body, for example, around a planet. So the atmosphere of a planet assuming the temperature of the gas is the same everywhere. So it's an idealized situation. This is not how the real atmospheres work, but it gives you a good idea of what the pressure will be as a function of height in the atmosphere. And the traditional way of doing this would be to imagine you have a small slab of atmosphere of HDH, and then there's a certain gravitational force on this slab due to its density, and you have a small pressure here from the layers below, and you have another pressure from the atmosphere above, and these three forces, the pressure from above, the pressure from below, and the gravitational force, have to balance out, because we want to know what's happening when the atmosphere is in equilibrium. So basically this thing doesn't move. And we also use the fact when we derive this that the pressure times the volume is a constant, so that's Boyle's law, and so on. And in a few steps you can derive the pressure as a function of height in the atmosphere. And now we will do the same using the Boltzmann distribution. So what do we have here? So we have the same situation. We have an atmosphere, particles that are in a gravitational field, and the energy of a particle in a certain state. So what describes the states of the particle? But a particle can have some position and some momentum. And the positions, well, we will assume spherical symmetry. So the only important parameter that distinguishes the particles that describe the states of a particle is its height above the ground, which we'll call h. So the energy of a state I, it's equal to, well, the first one, mgh, when m is the mass of the particle. And then we must add a term due to the kinetic energy of the particle, plus p squared over 2m. So the probability of a particle being in a state that has this energy is proportional to a to the minus beta mgh plus p squared over 2m. Now, what we want to know is what's happening as a function of height. So we don't really care about the kinetic energy of the particle. So what we can do is we can integrate this term in the energy. So basically we can, because this exponential can be separated into two, so we have that the pressure is proportional to, not the pressure, but the probability of the particle being in a certain state, proportional to a to minus beta mgh, and then using the property of exponentials, minus beta p squared over 2m. And now what we do is, because we want to know the dependency of on height, we will integrate over all the momentum states. And as we see here, the momentum states don't depend on the height, the energy. And why can we do that? It's because we assume that everything is a constant temperature, so the momentum distribution of the particles will be the same whatever the height we are at. So with the probability of being at a certain height h is proportional to the exponential of minus beta mgh after having integrated over the momentum. Now, we know that the pressure of a gas will be dependent on how many particles there are. If you double the number of particles and they all have a certain speed distribution, twice as many particles by unit time will hit a surface, which is basically what the pressure is. It's how many particles will hit on the surface and be reflected as a function in a given unit time. So the probability of being at state h is proportional to the pressure, is proportional to the exponential of a minus beta mgh, which gives us that the pressure, I will put an R just to distinguish it from the probability, the pressure is proportional to E to minus mgh over kb t. And if we do the classical calculation people have been doing with the mechanics, we will get the exact same result. And this is obtained simply using the Boltzmann distribution by assuming that our atmosphere is in thermal equilibrium in a few lines. The second example will be paramagnetism. Paramagnetism is a property of many substances that are slightly attracted by magnets. I don't mean the attraction between a magnet and iron, for example, which is called ferromagnetism. This is a very strong attraction. Paramagnetism is much weaker, and it's caused by unpaired electron in the atomic structure of the matter composing the object. So in this example, I will take a very simple model of paramagnetism in which you have a certain block of a substance which has a density of atom n0 atoms per unit volume. And we will suppose that each of these atoms has an unpaired electron. So we have the atom here, we have the electrons, and there is a single electron here that is unpaired. And of course, this electron can have an up spin or a down spin. Now, this electron has its own magnetic moment, which will give a magnetic moment to the whole atom. So each of these atoms, due to this electron, will have a magnetic moment mu. Now these atoms are stuck in position. We will presume we have a solid here, so we can identify where they are. We have the classical assumptions required for using the Boltzmann distribution. And also, each of these atoms, all these atoms are in thermal equilibrium with each other. We'll assume they are weakly interacting, but they are interacting enough that they are in thermal equilibrium with the other, the magnetic moments are in thermal equilibrium with each other and with the other degrees of freedom of the system. So what can we say now? We put this block in an external magnetic field H, and well, each of these atoms can have, due to the quantum mechanical nature of the system, can have its magnetic moment aligned with the magnetic field or in the direction opposite the magnetic field. So we will denotate the aligned state with the plus and the inverse, not aligned or anti-aligned, with the same sign minus. So we know that the energy of a magnetic moment in an external magnetic field, in the case in which they can be only aligned or not aligned, is the energy of plus or minus is equal to minus the magnetic moment times the magnetic field. And the sign reverses because the energy is minimal when the atom is aligned with the magnetic field. Now we have a system of many atoms in thermal equilibrium, so we can ask ourselves, what is the probability that an atom will be aligned or not aligned? So we know that the probability of being aligned or not aligned is equal to the exponential of beta mu h, so that's the energy times our constant beta, And the signs here are reversed because there's a minus in the Boltzmann distribution formula. So this is not equal but proportional. So we want to know what is the magnetization of a single atom on average in our volume. So we will have that the magnetization is equal, well, a magnetic moment times the probability that the atom is aligned plus the magnetic moment in the not aligned case, which will give us a minus sign, minus mu, the probability of the atom not being aligned. And if we want to normalize all this, we will divide by the probability of aligned plus the probability of not being aligned, which will normalize our distribution. Now we can replace our P plus and P minus by what we had here, and we will have that the magnetization is equal to mu. And if you do the whole calculation, we will get the hyperbolic tangent of mu h over kb t, where the hyperbolic tangent is defined as with the exponentials so the exponential of x minus the exponential of minus x divided by the sum of these two terms. Now, if the temperature is relatively large, this term is large compared to this energy, then we can approximate the hyperbolic tangent by noting that when x is pretty small, I think I will do this on the next board, because now it's getting really cluttered. Okay, so back to our calculation, because this was getting really cluttered. When x is small, the hyperbolic tangent of x, which is equal to the exponential of x minus e to the minus x over e to the x plus e to the minus x, becomes equal to about 1 plus x, which is basically e to the x when x is small is about equal to 1 plus x to by the Taylor series. And there are other terms. I don't keep them because they will cancel out. They would not be required, but I know what I can keep the term in x squared over 2, just to make it very clear that these terms are not useful. And then minus 1 minus x plus x squared over 2, so on. And divide the same thing here with the plus, so it's this term here and this term here. There's a plus in between, so I would kind of write that one plus x squared over 2 plus 1 minus x plus x squared over 2, and so on. We will see that these other terms don't matter. So here the ones will cancel out, and x minus minus x will become x, and the term in x squared will cancel out. And all these terms that will remain will be terms in x cubed and so on. And when x gets small enough, we can neglect them. So this is equal to 2x over, now the 1 and the 1 here will add to each other, so it will be 2. And the x and the minus x will cancel out. And then we have terms of order of x squared, and we just neglect them when we get to the very small values of x. So when x is very small, hyperbolic tangent of x is equal to x. So basically what we get now, if we get back to our previous calculation, we will get that the magnetic moment on average of a single atom would be equal to, let me see, mu h over kt. K is the Boltzmann constant, and if we have a certain density of atom in a certain volume, we will get that the magnetization per unit volume is equal approximately to the density of atom times the magnetic moment times h over kbp. So we get two results here. The first one is that the magnetic moment, so the magnetization is proportional to the magnetic field, which is a classical result about linear materials and paramagnetism. And we get that this constant, which is a constant for a given material at a given temperature, will have an inverse relationship with temperature, which is called Curie's law. So that's the second result I wanted to present, showing that paramagnetism can be described easily using a very simple model and a Boltzmann distribution. And that's it for today.